Oh, never mind. I'm being recorded. I can't get signal. All right. So here we are for the second semester, right? Since the class average was so low, they moved us to the other building to kind of knock us. I'm joking. It's like I said, different time of the day, and this is the classroom that's open. So what can you do, right? Anyway, second semester is in a lot of ways the same as the first. The difference kind of being, I guess, that maybe now you guys are a little bit more used to the language of organic, right? We spent a lot of time kind of dealing with the mechanisms and the arrows and looking for our positives and looking for our negatives and kind of all that stuff that kind of goes together with those concepts. And the second semester is just kind of more of that, right? Just figuring out some more reactions and how we can do transformations for different functional groups. The focus, I guess, or the main ideas that we're kind of going to hit in the second semester here is a little bit more on the synthesis side of things. So how can we start to string together a series of reactions to come up with a new molecule or a bigger molecule or a better molecule or whatever you want to say with that, right? And so if you think back on it, what we did in OChem 1 was, here is a functional group and how do we transform it into another one, right? We did a lot of these single step type of reactions, right? And so what we want to kind of build into at the end of this semester is, now that you guys can do one reaction, can you guys do 3 reactions? And you guys are like, no. But so on paper, it sounds kind of easy, right? If I can do one, if you can take one step, then you can take one step 3 times. But the idea that we have to start to pay attention to is the selectivity of some of these reactions. And we started to talk about this a little bit at the end of last semester, where we discussed, with an alcohol that it can act as a base and an acid, right? And depending on the kind of acid you put in there, a different product comes out of it, right? Whether you use sulfuric or hydrochloric or hydrobromic and all that, right? We have a different transformation that can get affected by each of those other reagents that we put in there, right? And so that's the kind of idea that we're going to play into as we move through the semester, because what we're going to learn is a bunch of reactions, okay? Just a ton, right? I have this functional group, I can transform it into this functional group. And there's going to be a lot of them. How do each of those different reagents that we use in those transformations, how do they react with other functional groups that may be present, right? Because if you take a look at the top 10 most sold pharmaceuticals, for instance, right? It's not just a compound with a single functional group, right? Very rarely is it that. So how can we adapt? How can we take care of these different functional groups to actually do the transformation that we want? So that's the kind of thing to start to pay attention to, right? Always start to ask the question, what's next, right? What else could I do with this? What could this functional group that I want to make start to react with, right? That kind of idea. And we'll start to build into that a little bit too, right? And so if you remember where we ended up last semester, we also talked about the idea of protecting groups a little bit, right? And I think we talked a little bit about the protecting groups for alcohols and what it actually means to be a protecting group, right? So we'll come in and talk about those quite a bit more, and just how we can add those or remove those or do something different with all those different individual groups there, okay? But where we're going to pick up, we're going to kind of hop back into chapter 12 and finish up some of the alcohol chemistry that we didn't get around to, just because I think it lends itself a little bit more to the second half. We spent quite a bit of time dealing with alcohols in the first semester and quite a bit of time dealing with the halides in terms of eliminations and additions and substitutions and all that kind of stuff in there. And so we're just going to kind of pick up from that exact same place there and just kind of keep moving forward with it. But the first big thing that we need to talk about, or kind of the first big topic we're going to hit is dealing with how to make ketones and aldehydes and some carboxylic acids, right? So we're going to take a look at oxidations and reductions. And that's going to be important, and then we're going to kind of leave those alone, and we're going to step into the realm of aromatics. Now, aromatics are things like benzene and some of the derivatives of benzene there. And if you remember, one of these things that I taught you guys in the first semester of organic is that benzene doesn't do anything, right? We just left it on its pedestal there, and we said we're not going to react or do anything with it, right? So now we can throw all that out the window, okay? So then, so everything that I taught you, right? How much did you guys pay for this class? All right. Okay. But now we're going to come in and we're going to start to do some reactions with aromatic rings, and you'll see that actually in reality they're quite reactive under specific conditions, though. Okay. So we're going to learn those conditions. We're going to learn how to do quite a bit of transformation and additions and eliminations and substitutions and that kind of stuff on our benzene rings themselves. And then after we go through that, which is about 2-ish or so chapters, then we'll come back to carbonyl chemistry again. And pretty much the rest of the semester at that point is all carbonyl chemistry. Right? So we spend like 4 chapters dealing with carbonyls, right? And the different derivatives of that stuff. So we'll end up learning, what is it? Let's think here for just a quick second. So 1, 2, 3, 4, 5, 6, maybe about, I would say maybe about a dozen or so new mechanisms, right? So not too many new mechanisms in the grand scheme of things, but you guys will learn a lot of different reaction conditions. Right? So what we're going to see is kind of the same idea that we saw happen with OChem 1, wherein I taught you guys an SN1 mechanism, right? And I taught you guys an SN2 and an E1 and an E2. Okay. But you see those same steps that were repeated over and over again in other bigger mechanisms for different reagents and different reactions. So the same thing here. We're going to learn how carbonyls react, okay? But we're going to see that same reactivity and that same pattern happen over and over and over again in different sets of carbonyls, okay? So that's kind of how it's going to be, right? So we have the broad picture there. We'll start with the alcohols. We'll talk about oxidations. We'll move into the aromatic chemistry, and then we'll move into the carbonyl chemistry. And then depending just kind of how far we get and where we kind of end up, we might talk a little about organometallic chemistry, just kind of some of the modern, I don't know if modern is the right word, but let's say the coupling reactions and how different transition metals actually do a lot of the chemistry a lot easier than what I've been teaching you guys. I'm teaching you guys the hard way to do it. Sorry, okay? If I taught you guys the easy stuff first, then the exams would be all easy, right? Oh, this is one step, I can just blah, blah, blah. And then I have to give you guys good grades, right? I don't want to do that, right? Yeah. No, I'm just kidding, right? But we'll talk a little bit about how transition metals do some very, very unique chemistry as compared to what we've seen before, okay? Other than that, everything's kind of going to be about the same as what we did in the first semester there. We'll have a couple of exams and have a couple quizzes and this kind of stuff. Just don't get sick and then we don't have to do anything, all right? Okay, there we go, right? We're all here, we all do the quizzes, we all do the makeups, all this kind of stuff. We do have lab on Thursday, right? We'll start off a little bit easy because we always got to do the safety stuff on the first day there. So we'll make soap, okay? How many of you guys have made your own soap before? 2 of you guys. The rest of you guys are screwed in the apocalypse. All right. Man, all right. So we'll make some soap, and then we'll make some raspberry fragrance, I think, to go with it for the second lab. So we'll see how that goes. It's a new experiment, at least making the raspberry stuff there, but who knows? We'll see what happens. You guys are very good at it, so you guys are, impressed me mightily with your ability to make benzocaine, right? So, but anyway, we'll see how the lab goes there with that stuff then. But guaranteed, I will guarantee that all of you guys will be able to make your own soap. Whether you actually want to use it or not is a different argument. But that's all good. All right, so labs, and then you guys know about the exams. Will be during the lab weeks there too. And if everything goes as planned, I'd rather have all the exams in person rather than online stuff, just because then the exams are easier and you guys don't have, you only try for 2 hours instead of 20, and life is a little bit better, right? So, but no, in-person exams are always going to be easier, right? So, but anyway, it's just kind of I don't know. It's a better measure, I guess, of some things, but that's a different argument for a different day. All right, sound good? Any immediate burning questions then? Or? Yeah.
Are we going to have to remember how to do radical reactions at all this semester?
Yeah, sure, that sounds good. I mean, we're not really going to see that mechanism come back again. I think, yeah, off the top of my head, I don't think we do anything more with radicals, although the halogenation, like radical halogenation, is always going to be a good synthetic step, right? To add a functional group, right? So in terms of that, definitely keep it in mind, but I don't think we're going to see the radical mechanism again, specifically. That was your question? You were waiting on that one for 6 weeks, right? Like you're over there at Christmas, like, come on, I gotta ask you, right? That's all good. Anything else? Or? Cool. All right. Well, you had your chance to stall for time there, but I guess you guys like, no, we want organic chemistry, right? All right. Never make it easy, right? All right, have at it, guys. See what you guys remember. And for every question you get wrong, I have to play the piano. What you don't know, you can play the guitar instead. It would not sound good.
Andre, I have a question now.
Yeah.
How did you come up with the name on canvas?
I'll show you. Ask me after class. I'll show you. It's a very complex thought process, right? It needs time, but I'm just kidding. I'll show you. I mean, tell me I'm wrong, though. It's an apt name, right? I mean,
No, I
yeah.
think that should be better than organic chemistry too.
Yeah, that's a good point. Like, organic chemistry sounds scary, right? Drawing hexagons, like, yeah, I can do that. Crap, a pentagon, I'm going to fail this class.
No, the real question, or the real struggle would be the heptagon or the septagon. That is the real struggle.
As with all things in life, practice. Was thinking about doing the first week quiz. Much like the Grinch, my heart grew 3 times. I'm just kidding, I got lazy. I'm like, yeah, I'll do it. Probably Wednesday, that sounds good. A little bit of time to nap the rest out. You guys could read the ingredient bottle on here now, right? There's octyl, decyl, right? Dimethyl, ammonium chloride, right? Yeah, those are words I know. Dioctyl, dimethyl. Anyway, I'm distracting you guys from your work. Let me judge partially. Let's see. Nothing. Yeah. Also nothing. Double nothing. Yeah. Oh man, this is gonna be a long class for you guys. Nothing. All right. And now somebody happened to ask a question about what we need to do here. And Annie asked, well, what do we need to know about? That's not what you asked. What's the problem that we have though? So we start out with just a plain old hexagon, right? Our good old buddy cyclohexane. You guys remember how to draw chair conformations? No. You guys remember axial and equatorial? Right? All this kind of stuff. Right? But we don't have a functional group there, right? So we need to add a functional group. So what's the reaction that we learned on how to add a functional group? Only one of them, and it took a whole chapter to figure it out. A chapter that was quite radical in what it showed you there. That was a hint. It was subtle, but I worked it in there somehow, right? Aha, our radical halogenation. So if I present something that doesn't have a functional group, right, then we need to add a functional group to it. And one of the, say perhaps the most studied, or maybe what we studied the most in OChem 1 at least, is what we can do with halogens, right? What can you guys do with a halogen? Can you eliminate it? Sure. Can you substitute it? Sure, right? So we know quite a lot of chemistry that we can do with halogens, so it'd be a good idea to maybe add one there first. How can I do this? Well, I gotta have a halogen source, and I gotta give it some energy to form the radicals, right? Good? Now I've got a functional group. Now can you guys turn that into an OH for me? So, what do we have to do now? So we've got an alkyl halide, right? We can basically do two things. We can either eliminate, or we could substitute, right? Which one do you guys want to do? Okay, so we want to do a substitution at a secondary leaving group, right? Okay, well, what's our two mechanisms for substitution? SN1 and SN2, okay? So which one's going to be favored at a secondary position? SN2. Why? What do you mean? I know you memorized my two smart answers. In fact, I think you got a new tattoo or a stare and then electronics. She's cheating on the exam. What do you mean by stare, sir?
I guess since it's secondary, you can have a cargo cutout on it,
Well, you told me about Sterix, and then you went and made an electronics argument, right? Because you're talking about carbo cataracts, which is important, right? I'm not saying that you're necessarily right or wrong with that, but go back to your idea of Sterix. What is Sterix?
since it's secondary, there are two things coming off the carbon, so it's harder for it to happen in one step because they're not like they're atoms in a way.
Right, so Sterix is how much stuff is there around our leaving group, right? Or our functional group, or whatever it might be, right? Remember, one of those key important things to pay attention to is our functional group, no matter what it is, right? Whether it's an alcohol or a halogen or a ketone, or, right? Is it a primary, secondary, or tertiary position, right? That's always one of these key things to pay attention to. So we have a secondary leaving group here, right? Because the bromine is attached to a carbon, and that carbon is attached to two other carbons, right? So remember, we're always looking at kind of what's next door, that kind of spiel there, right? So what is next door to that red carbon there, right? There's two other carbons there, so a secondary leaving group. So can we do an elimination at a secondary position? You bet. Can we do a substitution at a secondary position? Yes, we can. Okay. So all of our doors are still open, right? We can do a substitution, we can do an elimination, that's fine. Well, what do we want to do? What does it look like we want to do, I guess I should ask. Okay, so it looks like, let's say that we want to try and do a substitution. What are our two options? SN1 or SN2. Okay, so now let's say I want to do an SN2 at a secondary position. Okay, so what do I need to do an SN2? I need to have a good leaving group. Do I have that? Yeah. Can I do SN2 at a secondary? Sure. What else do I need?
Strong acid.
Hmm?
Strong acid.
Go ahead.
Well, at a secondary position, there's that E2 needs to still happen, so don't you have to make it like that E2 wouldn't happen, but S2 would be favored.
That's a thought. So hang on to that. If I wanted to make an SN2 happen, what else do I need? Not a strong acid. Somebody else said what?
Strong base.
Okay. Is that how SN2s work?
No, it's
A substitute. What's the N in SN stand for? 2. So what do I need? A good nucleophile, right? Okay. Well, I need to put an OH there. What's the best nucleophile I can make with an OH? Well, to make a good nucleophile, right, I'd have to bring in the functional group with a negative charge, right? You guys get what I'm saying with this? What's a good nucleophile? Something that has a delocalized negative charge, right? That's kind of spread out. A weak base is a very good nucleophile. So is that a good nucleophile? Yes, it actually is, right? But what is it also? A very strong base, okay? So what's going to be faster, what's going to happen quicker? An acid-base reaction. So, here at a secondary position, right? Got a secondary leaving group with a strong base. We're probably going to have a pretty decent mix here of substitution and elimination, right? Will this do substitution? Sure. Will it do elimination? Sure. What's the mix going to be? 50-50-ish maybe, right? Maybe a slight preference for elimination, depending, right? You do it a little bit colder, a little bit hotter, something to think in there. At the end of the day, we kind of make a mess. is what we're saying, right? So maybe not the best route. So maybe we can't do SN2 yet, right? Okay, can we do an SN1? Well, do we have a good leading group? Sure. Can we do an SN1 at a secondary position? We can, but what's the problem? Carbocation's gonna suck. We make a secondary carbocation. Can we make secondaries? Sure, but they're not very stable. Which means what?
Saying like 50-50.
What do you mean?
Like, we're not 100% sure he's gonna form all the time, like.
Maybe, right? Maybe, but there's something else. There's something else that's kind of at play here. Okay? Go ahead. Ah, okay. So remember, every time that we make a carbocation, we have to pay attention to shifts and rearrangements, all that kind of stuff, right? So fortunately, in this case, we're not going to see any of those, right? Let's see, can we do a ring expansion or something? We'll come up with something to, really lay it on thick next time for you. But no, all right, none of that stuff here, right? But that's always something important. Every time you do a carbocation, look for shifts and rearrangements and all these kind of things that can happen, right?
Could you do like, can you force an elimination?
So hang on to that thought. Right, I like where you're going, but pause for just a second. I'm doing an SN1 reaction. What does it mean to be a 1? What does the 1 in SN1 mean? Hmm? Unimolecular in the rate determining step. Okay, what is unimolecular in the rate determining step? Well, that's great. That means it's a step that determines the rate. There is only uni molecules. Right? Now, what does that mean? What does it mean to be unimolecular in the rate determining step? It means the slow step in the mechanism, right? Only has one molecule in there. Okay, fine. What's the rate determining step for any SN1 reaction? Formation of the carbocation. Perfect. Is this going to make a very stable carbocation? No. So what does that tell you about the rate determining step? Extremely slow, right? To the point where if we want to do an SN1 here, you'd mix the stuff together and you'd wait, right? And you'd come back next week. It still hasn't done anything, right? You come back the week after that, maybe a little bit happened. You come back the week after that, and somebody knocked over your reaction, right? It's just not going to happen at any practical speed, okay? Can it happen? Sure, right? Because remember, what's one of the benefits? Well, you guys are doing chemistry on paper, right? Time isn't really an issue. But it is something to pay attention to, right? SN1 reaction at a secondary position, extremely slow, right? Extremely slow. Okay, so we can't really do SN2, we can't really do SN1, which then we're in the realm of eliminations, okay? So now, let's see if we can go walk down the path of eliminations. So see what you guys come up with. What do you remember for your eliminations? E1 and E2. Okay, cool. So we can automatically throw one of those out. Which one can we throw out? Why can we throw out E1? It's too slow, right, because it has a formation of a carbocation with that, right? So if we couldn't do an SN1, practically speaking, we probably can't do an E1 either. So we can't do E1, we can't do SN1, we can't do SN2, which leaves us with nothing. Go home, right? No, I'm just kidding. Okay, we got it. All right, so we'll do E2. So what do we need? What's the recipe to make to do a good E2 then? Well, we need a good leaving group, right? Do we have a good leaving group? Sure. Okay. And now we know what flavor of leaving group it is, right? We've got secondary. All right. What else do we need then? Strong base. Okay. So what could be a strong base? Well, you guys are welcome to pick whatever you want, right? But I think we always kind of, there it is. We kind of always used some of these O's with negative charges, right? Our eth oxide and ethanol, right? Our acid, Lewis acid base, Bronsted acid base pairs there, right? Eth oxide, so alkoxides in their corresponding alcohols, right? What's up?
Is that like LDA or something?
Yeah, we could do that too, right? LDA, butoxide, any of those, right? Anything with a strong base. So, what's my next question to you then, you guys? What is a strong base? Right? It's a strong base. A localized negative charge. Is that negative charge localized? How do we know? Well, how do we delocalize things? Spreading it out. Do we have different ways of spreading things out? Sure, right? Resonance, inductive effects, electronegativity, radius, right? All these different things that we talked about in the acid-base chapter in OK1, right? Do you guys all remember? It's extremely important. I told you guys, that acid-base chapter is probably the most important chapter that you guys take in organic chemistry. Because it all has to deal with looking for charges and how do we stabilize and spread it out and inductive and all that kind of stuff, okay? That stuff comes up over and over and over and over and over and over and over again. Acid-base chemistry is one of these foundational steps in all of chemistry, okay? So, we got a strong base, we got a good leaving group, it's secondary, all that kind of stuff, right? Blah, blah, blah. Right, we grab a hydrogen next door, get that off. Okay. Good. Now we've got a pi bond. What can we do with pi bonds? A lot, right? What do we know about pi bonds? Well, they can act like nucleophiles, right? That's something we learned. Like, yeah, of course, Doctor. That's nucleophile. What's it mean? What's it mean to be a nucleophile? What's it mean to be a nucleophile?
You want to go after positive charges.
You want to file some nukes, right? What's the nuke? Well, that's nucleus, right? There's some positive stuff there, and if you file something, you like it, right? So you're going after things with positive charges. Why would a pi bond be a nucleophile?
Because there are electrons on the bottom.
Is that what you're going to say? I don't think so. I'm trying to say. You just say that. No, that's it, right? How, what is the only thing in the world that likes positive charges? Electrons, right? And we've got a pi bond there, and remember the density, electron density of a pi bond is above and below the plane. Right, so we've got these pi bonds, the electrons that are hanging out above and below the plane. And if they act like a nucleophile, we can turn a pi bond into a sigma bond, which is downhill in energy, right? That's a favorable thing to do, right? So there's a lot of good things that come out of having a pi bond act like a nucleophile, right? So we can do an addition reaction with these, right? We can add things to them. Now, I think we'll learn something this semester. Yes, we will. Yes, we will. In fact, I don't remember. Right? We will learn how pi bonds can act as electrophiles also. Right? So in some cases, we'll see how pi bonds can act as electrophiles. So if I ask you guys a question, what's a nucleophile? Well, those are things that like positive charges. Right? Electrophiles are things that like negative charges. Right? So we'll talk a little bit about how pi bonds can behave in that way. Okay? But for the moment, all we really know what to do with them is an addition reaction. Okay? Make them act like a nucleophile. So, can I turn an alkene into an alcohol? Yes. How many different ways do you guys know how to do that? At least 3, right? Who said 1? I heard it. You're looking guilty. It was Ian, you called him out? Oh, that's so rude of you. You can sit up here. They're like right there. Right? But we know quite a few different ways of turning an alkene into an alcohol. Now, not all of those different ways are equal, right? We know how to do it through the addition with a carbocation, right? We can do sumo mechanisms to add them. Right, or oxymercuration, demercuration, right? Yes? What's the benefit of the sumo mechanism? No carbocations, so no rearrangements. Got it? Okay. We know how to do our hydroboration oxidation. What's the benefit of that one? Okay, right, we have anti-Markovnikov addition, right? Anti-Markovnikov addition of an alcohol. Does it matter in this case, though? No, they're both equal. So could you still do the hydroboration here? Sure, right? There's not a less substituted side, right? So pick your favorite way and you can get it done in this case, right? Me, I want to save calories, so I'll write the least amount that's possible, right? So we could just put a simple acid catalyzed hydration, right? Good? Would that work? Yeah. It would on paper. Right? In reality, we wouldn't want to do it that way, but that's a different argument for a different day, right? Cool. So, quick question. Serious question. What if I had given you guys that as a quiz today? How would we have done it? Why is that? Yeah. Just being honest with you guys. If I can have a little bit of serious talk with you guys. I spent a lot of time teaching you guys Automotization, right? I think I know I did a fantastic job. Just said serious time and crack a joke like 30 seconds. No, serious, come on. Right? But anyway, in all seriousness, I spent a lot of time, and you guys put a lot of time into it also. I expect you guys to know all of Automotization, right? That's just the way it is. I don't have time to go back and review it for you guys. I don't, right? As you guys know, there's already a lot of material that we have to cover, and I'm adding on to the stuff that we learned in the first semester there. So things like acids and bases and nucleophiles and additions and all that, right? Definitely stuff that we have to remember. And I think you guys remember more of it than you might be willing to admit, right, at the moment, right? But we do need to go and refresh it a little bit there, right? So I think I posted, like I think it's like a 3-hour video, kind of like everything you need to know from OChem 1 type thing, right? Put it on in the background, put it at 2 times speed, and just kind of, listen through it as you can, right? And when you get to a point you're like, I don't remember any of that, then go in and slow it down, right? That kind of thing. But, knock the rust off with these things. Because we are going to have to know these things. We are going to have to use these ideas over and over again. Because you remember I made you guys a promise. Right? Do you guys remember what that promise is?
We can read our shampoo bottles.
Yeah, I did. You're right. You are absolutely right. How many of you guys read your shampoo bottles? There you go, right? Did you understand a little bit more of it? Yeah, right? Yeah. It said water in there. I got that one down there. There's something called fragorants. Anyway, all right. But anyway, that is one of the promises, and I made you guys another promise, and that said that I would only teach you guys stuff that you would need to know, right? Something we would see over and over again, right? I'm not going to sit here and just load you guys up with fluff, because what's the point with that, right? You guys aren't necessarily chemists, although some of you guys are biochemists, right? But a little bit of a different, a little bit of different side there, but my promise still stays here. I'm not going to teach you guys anything that you don't need. On the other end of that promise, then, I expect you guys to know the stuff that we have gone through, right? I'm boiling this down as much as I can for you guys, but we do need to make sure that we remember this stuff from OK1. Fair enough? Good? Cool. All right. So now we have our good old buddy, an alcohol there, right? And so if we just put this guy, let's do this actually. Start over here. Okay, so then we can start. We have an alcohol. What do we know about those? Go ahead.
Hydrogen bonding.
So they can hydrogen bond. Now, where is that important? The answer is everywhere, right? And so, in fact, when I was starting Gen Chem 2 lectures today, right, we started talking about the intermolecular forces, and I told them that the first day of class in OChem, I would ask them what the intermolecular forces, because we'd see them over and over and over and over and over. And you know what they did? They yawned at me, because it's an 8 a.m. class, right? So, hey, don't worry, I'll get them yet, right? But anyway, so hydrogen bonding is always something important. We talked about solvent effects when we were talking about slowing down or speeding up SN1 versus SN2 and all these kind of things that went with it, right? So definitely always something useful to pay attention to there is the idea of hydrogen bonding. Okay? What else? They're terrible leaving groups, right? Alcohols, OHs, O's with a minus charge, are terrible leaving groups. Now, we will see an O minus act as a leaving group this semester, but there's something else that's going on behind the scenes, right? That's something good to remember. Now, as a quick tangent, can we turn an alcohol into a leaving group? Yes, all right? We have a couple different ways of accomplishing that, right? We'll cover a couple of new ones here at the beginning, although some of you guys ran into these already when you were last semester, but that's okay, right? So they are terrible leaving groups, but we can transform them into good leaving groups. What else? We have an acidic hydrogen, right? What's the relative pKa of an, I should be careful. What is the, let's say, the pKa to remember for an alcohol?
16.
About 16-ish or so, right? So that's pretty good, right? So if you remember about 16, that kind of gives you an idea, right? Although, can we make alcohols more acidic? Sure, right? Can we make them less acidic? Sure, right? But pretty good to kind of remember that way. What else? We talked about acids, so it might be good to think about. Right, there's lone pairs on the oxygen. Like, remember that alcohols can be amphoteric, right? So they can act as acids and they can act as bases, right? Are they good acids? Is a pKa of 16 a good acid? No. Are they good bases? Not particularly, right? But can they act as acids and bases? Sure. Can an alcohol react with a strong acid? Absolutely, right? Absolutely. Can an alcohol react with a pretty strong base? Absolutely, right? So that's something, those are some important points to remember there. Now, we talked about how we can transform an alcohol into a tosylate, right? We put in some tosyl chloride and some pyridine, right? And then it turns into a good leaving group, right? We talked about, we talked about the trimethyl silo protecting groups, the TMS chloride. Did we talk about that?
I think it was
Yeah. I think around, yeah. So we talked about how we can protect the alcohols, right? So when we have to be careful about what reagents we're adding in there, right? We have our TMS, our trimethyl chloride, right, is a protecting group for alcohols. That means they're not going to react in the same way, right? So they're not going to interact as much with the acids and the bases. That's good. But what we're going to talk about now is something we didn't really mention too much in the first semester, although we kind of saw them along the way, right? So what we're going to talk about first are those, okay? What's that? Let's see, -2 for Amy, -2 for, who else said it? Not a ketone, but an aldehyde, right? It is a carbonyl, closely related to a ketone. I have a lot of people say, I'm just picking up. You're sitting here, and I like to hang out on the left-hand side. Oh, okay. Any intention is good, Dr. Rich. You don't understand. Oh, man. Right? So we talked a little about aldehydes and ketones, right? But here we have an aldehyde, right? How do we know it's an aldehyde? Carbon on one end, hydrogen on the other, right? So aldehyde. Can you guys make an aldehyde already? Yes, you can. One very confident person. All right, Taylor, we're looking at you. How are you going to do it?
I'm being honest.
Yeah, that's okay. The answer is true, right? You guys did learn how to make an aldehyde. It was a kind of a roundabout method here, right? And the way we kind of learned how to do it is if we had, let me draw this a little bit better. Well, I already gave you guys a hint. So I used to bring a bag of Jolly Ranchers to incentivize you guys, right? Like if you say something like, oh no, it's like, who's got the answer? Right? But then apparently I wasn't like, they forbid us to give out candy and stuff at other schools, so I just got out of the habit, is what it is. But, so we have a terminal alkyne, right? And you remember that something weird, maybe not, I shouldn't say weird, I should be careful. Something unique happened when we dealt with the addition of alcohols to alkynes, right? So we remember that if we, let me go give myself a little bit more space. BH3, right? THF. We come in with some sodium hydroxide, H2O, and some peroxide, right? I studied my flashcards. Right? So if we're doing our, hang on just a second before you guys copy down everything, right? So if we're doing our hydroboration oxidation, right, we add the alcohol. Let me put some color in here real quick, right? So there's the blue, there's the red, right? So we add our alcohol to the less substituted side, right? What did we say happens from this point? Right? We have an alcohol attached to an alkene. Right? This was a question on your guys' final exam, right? I believe, if I remember correctly.
Does oxygen always just want to have two bonds?
Right, so hang on to that thought, yeah. So that's going to be very important in just a minute, right? But remember, when you see an alcohol coming off of an alkene, it's going to tautomerize, right? So there's going to be a tautomerization. Wherein, what we will actually end up with is this, right? H, E, and okay? Can't stop it from happening. Now, you'll notice my arrow in pink. Does it look a little bit fuzzy, or is that just my worsening eyesight? Maybe it's the... What am I going to do anyway? Go up there and adjust the focus. No, seriously, the focus is up there. That's useful. Good. Jose, Jose, you're the tallest guy here, sorry. Get on Ian's shoulders and adjust the focus, right? Anyway, I don't know, maybe it's just me, but, right, we can't really stop this tautomerization from happening. So we will never end up with a double bond and an OH coming off of it. It's just going to instantly tautomerize over, okay? Now, it is an equilibrium, and what do we mean by that? You can go back and forth. It's just one side of this equilibrium is very heavily favored. The carbonyl side, the aldehyde side, is way more favored than the enol, right? So the enol, right? So the alkene with the alcohol, the enol side. However, the reason why I'm mentioning it here is because we're going to be able to use that enol chemistry in the upcoming chapters, right? So when I said we're going to spend about 4 chapters dealing with carbonyls, making an enol and then reacting it is going to be something that we see quite frequently. In fact, it's going to be a useful, I guess intermediate would be the appropriate term here, right? That enol, that transient enol intermediate there is going to be useful for us to do something. So I need you guys to remember about the tautomerization, right? Can you guys do the mechanisms to do that tautomerization?
Can you show it to us?
Can I do it? Is that what you're asking? Of course I can. That's not going to help you guys, is it? So let me help you guys out a little bit here, right? So let's just simplify for just a little bit and let's see what you guys come up with, right? All right, so ignoring the other things in there, sort of, here's what I'm asking you to do. In the presence of a base, right, and we have some water, can you guys show me how to get from one side to the other? Okay? Now, before you guys get started, right before I launched into this spiel about alcohols, I drew you guys the first alcohol, and what did we spend time doing? What are the properties of them, right? And so think about the properties when you come up with a mechanism for this here, okay? So see what you guys come up with. See if you guys can do a real quick mechanism for the tautomerization. So I think you guys 3 arrows, right? 1, 2, 3, 4. Excuse me, 4 arrows. Keep going with that. Good. So keep going with that. Good. No, you're on the right track. Just don't forget to make a bond then. Good. Oh, what's that? Oh, what are the fastest reactions there? Oh, interesting. Right idea with the arrows are going in the wrong direction. Remember, always from the negative to the positive, right? Okay, we'll go from there. Good. Do something here first before that happens. So give it a reason to want to do this. Right now it's just a Python, it's not like I want to do something. But, right, here's where you are, and here's where you have to end up. Right, so how can you get from here to there? Right, and then that, good, there you go. Okay, so here's where you are, and here's where you have to end up. How could you go from there to there? What's your arrows? Right? Arrows always go from the negative to wherever they're ending up, right? Okay, so you do that, and then you need to do what? Yep, gotta do something. What's that? Go ahead.
It's a base.
It is a base. Is it a good base?
Yes.
You bet. How do good bases want to act? Like a base. Okay? If you're a base, what are you on the hunt for? I asked, do we have something somewhat acidic in there? Sure. What do we have? An alcohol, right? Can alcohols act like acids? According to Dr. H, they can, right? Dubious source. Okay. Good. Anything unusual about this? Acid-base chemistry, right? Not too bad. Ooh. This, negative charge here, right? Like that. Cool. Now what? What's the problem we have to fix? We got a charge, right? Can we stabilize that charge in some way? Sure, right? We can stabilize it by turning a lone pair into a pi bond and turning a pi bond into a lone pair, right? Also known as a resonance structure, right? So let's do that. Black sounds good. We'll do this, right? And this. That was terrible. Much better. Good? Can you guys finish it up from here? Carbon with a minus charge. Darn powerful base, right? Do we have something that can give it a proton around? Sure, what do we have around? One. Got it? So, do one last acid base. Right, we end up putting that hydrogen there, right? Cool. Could you guys do this under acidic conditions? Yes, Dr. H. Okay. Remember, we're under basic conditions. What charges are there around?
Oh, wait, sorry. I thought we meant, never mind. I'm gonna stop here.
Okay. So, if it's not positive charges, what charges do we have around? Negatives, right? So if you're under basic conditions, making another negative is not a big deal, right? Very, very, very rarely will you ever see a full positive form under basic conditions. Can it happen? Yes. But there needs to be a good reason for it to happen. More often you're looking to make more negatives. You trade one negative for another, that's all it comes down to. Under acidic conditions, things are positive, so you end up making more positives, right? Very, very rarely will you see a negative form under completely acidic conditions where everything else is positive. Got it?
Wait, so this can happen with the stick conditions?
Oh yeah, this happens under any conditions. You really can't stop it. Because even in like pure water, there's just a little bit and enough of the acid and base around for this to happen. Right? You can trap the enol if you put the protecting group, right? You can actually stop this if you put the trimethylsilyl in there and kind of stop the acid base part from happening. And that's actually, there's a set of reactions. I don't think we'll learn that, but that is something you can do, right? It might even be in the book, but so you can stop it, but you need special conditions for that. As I spit everywhere, you can stop it, but you need special conditions. Under just regular, just acid or base with an alcohol, it's going to immediately go over to the tautomerize. Okay. Cool. All right. So it looks like we've got a clock that works in here, though, which is an upgrade from right. But we'll pick this back up and we'll continue working through a little bit of our carbon and that kind of stuff. Okay. We will see you guys on Wednesday.